All right, let's continue then. We've been talking about logs for a while. Today I want to talk about the exponential function, e to the x, right? We talk about logs first. Specifically, actually, all we've ever been talking about is the natural log. So we would like to talk about other logs eventually, but for now, I want to talk about, this is a little weird, but this is the way our book describes this. The natural exponential function. Most people don't call it that. But of course, everybody knows there are many different types of exponential functions. There's like 2 to the x, or 3 to the x, or e to the x. And e to the x, from the point of view of calculus, e to the x is like the nice one because it has nice properties. And for that reason, e to the x is sometimes called the natural exponential function, although usually we just call it e to the x. But anyway, recall, if you will, we start with the log, the natural log of x, which has this as its definition, 1 over t dt, right? And we talked last time about the graph of this. I will refresh our memory. It looks like this, all right? So here, ln x, can I just say in words specifically, this has domain and range, right? The domain here would be all positive real numbers. You're not allowed to plug in 0 or negative numbers. If I were to write that as an interval, it would be like this. The interval 0 to infinity, not including 0, that's the domain of this function. And then the range would be all the y values. And can we say what's the range of that? You can tell by looking at the picture. Yeah? Yeah, as an interval, I would write minus infinity to infinity, or you could just say all real numbers, right? Any y value can come out of there as the output of ln x. You can get any real number. Minus infinity to infinity is the range. All right. What's the definition of the natural exponential? I'm going to define it to be the inverse as a function, the inverse of this line. I hope you all know what inverse as of a function means. So we're going to define the inverse of ln x as, I probably should write, do you mind if sorry, I'm going to rearrange my words. I'm going to define, come on now, sorry. I'm going to call it this for now, exp. This is the exponential function, exp of x, to be the inverse of ln x. Sorry to rearrange on you. All right. I'm going to call the inverse of that, I'm going to call that exp of x. This is something we haven't talked about, but I'm sure you talked about it in high school. Can anyone tell me there is a way in general, if you have the graph of one function, what does the graph of the inverse look like? There's a way to find the graph of the inverse. Do you remember?
Just like switch the y's and the x's.
Yes. Okay, yeah, if you're working with equations, you would some people like to say interchange the roles of y and x and then solve for y again, or you could solve for x in terms of y and then write it as a function that way. That's true if you're working with equations. I'm just trying to talk about the picture here. How would I, anyone recall? Yeah? Yes, you would reflect across the line y equals x. So the inverse on this picture, you look at y equals x like this. Because the idea is you want to get the inverse, you just interchange the roles of x and y. And graphically speaking, what that means is like where all the x's used to be, you make those y's, and all the y's used to be, you make those x's. And that's equivalent to saying I reflect across this diagonal line. So this red one down here, that is ln x. And the other one is the reflection of that. Now, since this one down here has this approaching the negative y-axis, the inverse, when it goes over here, should be approaching the negative x-axis and then go up like that. So it looks like that. That looks pretty good. It's supposed to be the mirror image of the other one. Maybe it should be a little further down, like so, perhaps. All right? And this is what I'm going to call exp. That's the inverse function of the natural log. All right? Now, just calling it the inverse, we don't know all that much about it, although we can say one thing about it. You know, ln of x goes through x equals 1 here, and if I reflect it, then that means this, the exponential of x must go through 0 and 1, all right? So this is the definition of the exponential function. This is called, in this context, this is referred to as the natural exponential function. We all know there are other exponential functions too, but this is like the special one. This is the one that goes together with ln of x as its inverse. And this is called the natural exponential function. Now, we all know that this function also happens to equal e to the power of x, where e is that special number that we talked about last time. Can we explain why that is true? So, I would have you remember that this, what I described as a super important rule about the log, the natural log of x to some power, you can bring the power out front, r ln of x, right? I wrote this rule with different letters last time, I think, but I hope everybody is familiar with this. And also, what we remember also about the number e, and also remember e is a number with ln e equals 1. That's kind of the definition of e, right? It is the number such that this area under the curve ends up equaling 1, all right? So I would like to ask, what about, what if we do the natural log of e to some power? So that means ln of, if I did say e to the r, can anyone say what will this equal? Can use some of the business. R, somebody said r. Yeah, I think I agree. I would say use the rule for natural log first to bring the r down front. This will say r times ln e. But then I just said ln e equals 1, so this equals r, right? So the natural log of e to the r equals r. And here's a perhaps confusing magical step here. If the natural log of something equals something else, and I also have a name for the inverse, so I'm going to do the inverse function on both sides. My inverse function is called exp, right? That's the inverse of the ln. What happens if I do that on both sides? Well, on the left side, exp will just cancel the ln, because that's the whole point of what an inverse function is. So the left side will just say e to the r, and the right side will say exp of r, right? I'm not sure why I decided to use r throughout here. This is true of any real number, though. Exp of r is the same as e to the power r. So, writing it just like with an x instead of r, this function exp of x actually equals the number e to the power x, all right? So, let me just write this in words. So the inverse of ln x actually equals the x power of the number e, all right? This was not obvious at the very beginning when I just drew the picture of the inverse. You have no reason to think that that picture actually represents some number to some power, but it turns out it actually does, right? The inverse of the natural log actually is equal to some power of this special number e, all right? This is the intimate relationship between the natural log and this number e to the power x. So ln x and e to the power x are inverses. And from now on, I'm never going to write exp anymore. I'm just going to write e to the x. That is called the natural exponential function, or just the exponential function with base e. All right? So these are inverses. This is a useful fact, and it means that you can sort of go back and forth. You can write equations either as a logarithm or as an exponential function. So that means we can kind of interchange them. Not that they're the same. They're not, I wouldn't say interchangeable, but here's what I mean. We can interchange. For example, if I say ln of 2x plus 7 equals 5, this is just an equation. You might say this is a logarithmic equation because it has the log in there. This, we can write it, instead of using the log, we can write it using the exponential function. You just have to write it the other way around. So this says log of this equals this. The other way around would be e to the this equals this, right? These two equations mean exactly the same thing. They are two different ways of writing the same fact, right? It's kind of like, x plus 2 equals 5 is the same as x equals 5 minus 2. Whenever you have a plus, you could move it to the other side and use it to write a minus, right? This is the same idea. If you ever have the log of something, you can always kind of move things around to the other side and write it using an e instead of a log. And the other way around is true also. If you start with something using an e, you can rewrite it using logs. So this, in this context, this is sometimes called a logarithmic form of this equation, and this is an exponential form of the same thing, right? But we are just saying the same thing again, just writing it in a different way, all right? And this basic thing, here, how about this? What about e to the 3x squared equals 10? That's an exponential form. This is the same as, can anybody tell me, what's the logarithmic version of that? This is something that you will want to kind of get accustomed to. I show you the exponential version. What do you say?
Natural log of 10 equals 3x squared.
Yeah, I like that. ln of 10 equals 3x squared. You write it the other way around with the log, right? Generally speaking, if I have something like, e to the a equals b, and you want to interchange everything, you would write this as ln b equals a, right? This is, if you like memorizing things, you could just memorize the basic structure of that. But that's what I just did. Right here. All right, this is moving from the exponential form to the logarithmic form is super useful. All right, this is super useful for solving for x inside a log. What I mean by that is something like 12 equals 2 ln 10x plus 1. Solve for x. That's a plus 1 there. All right. It's hard to solve for x when the x is stuck inside of the log like that. But we can write this in the exponential format instead of the logarithmic, and then it will be fairly easy to solve. Now, I'm not immediately going to transform it in terms of this box. Really, using this box, really, it's more like it already looks like this, and I want to go back to the other way. Although, this 2 in front of the log really kind of messes everything up. Here, this is about just a log equals something, then you can rewrite it this way. What's a fella to do with the 2 here? It's not a big deal, but we do need to deal with it.
Can you just square the 10x plus 1?
Yes, this is not what I was thinking, though. There's an easier way to deal with the 2. Yeah? What do you say? Yeah, you can divide both sides by 2, although this would have worked, what he said before. You could push the 2 inside the exponent of the log, but that's more complicated. Let's do it this way. All right, and now we can do this, just write this again in the exponential form. So make sure everything goes where it goes, but this now will say e to the 6 equals 10x plus 1, right? I think I did that right. What used to go inside the log, if you look at the format of this thing, what used to go inside the log now goes on one side of the equation all by itself. And what used to be by itself is now inside the exponent of the e. All right, that's this. E to the power 6, That's just some number which you could do on your calculator if you really want to know what this is. But anyway, to solve for x now, I just would subtract 1 to the other side and then divide by 10. So this is going to be e to the 6 minus 1 equals 10x, and then divide by 10. So it will be e to the 6 minus 1 over 10, like that. There are other ways you could write this. And if you needed to find this answer, you can type that into your calculator. That's how we solve for x and this kind of thing. All right, you want to hear my hilarious math joke about this? Here's the math joke. Start with here. Can you solve this for x? The hilarious response. Anyone know this joke? Yes, I can. I can solve it. Nobody knows? With ease. Huh? You get it? Ease. Yeah. With ease. That's how we do it in Stag country. All right? So this is solving for x inside of a log. You turn it into an exponential format. Sometimes you have to do a little pre-processing. You really need, if you want to do this conversion here, you need the log to be all by itself. So you may have to do some stuff before switching it over to the e's, all right? And then you can also use this to solve for x inside of an e by switching it to a logarithmic. So let's just try one of those. So how about solving for x inside an exponent? That would be something like 4e to the x minus 2 equals 7. Can we solve this for x? Yes, we can. This time we switch it to the logarithmic. Now, again, we have to first just isolate the e part all by itself. So I'm going to divide the 4 as my first step. 7 over 4 like that. And now I write this as a logarithmic form. So this is the exponential format. I'm going to write it as a logarithmic, which would be ln 7/4 equals x minus 2. What used to be on one side by itself is now inside the log, and what used to be inside the e is now all by itself. All right, and then solve for x here, you just add 2 to the other side. So x is 2 plus ln of 7/4. And again, this is now appropriate to just type into your calculator if you need to know the answer there. All right, I got a couple of these for you all to try. See what you think. Your job is just solve for x both times. By switching it from one format to another. All right, see what you think. These are two separate problems. In each case, solve for x. Everybody's feeling good about these. Looks like everybody's feeling good with those. This first one, I would say, immediately you can write this logarithmically. ln 5 equals 2x plus 1. And then solve that for x. Subtract 1 and then divide by 2. I think it's going to say like that, right? Are you feeling it? And the other one, I need to divide the 4 first, because it's messing up the log at the moment. So ln 3 plus x is 2. And then write this as the exponential. It would be e to the 2 equals 3 plus x. So x is e to the 2 minus 3. That's how we do it. All right. Excellent. Great. Let's talk about some rules for exponents. These are rules that I'm sure everybody already knows, but I want to talk about them in this context. Rules for exponents. Like I said, I'm sure everybody knows these, but I will write down, I have 3 rules for exponents. E to the x plus y. Anybody know what can you do in this situation? This can be rewritten in somehow. Don't say e to the x plus e to the y. It's not that, but it's something. Yeah? Yeah, it's e to the x, e to the y, like that. This is a rule of exponents. This is not a special rule about e. It's actually true of any exponents. We all know you add the exponents in a situation like that. I got 2 others. There's also e to the x minus y is e to the x divided by e to the y. And then there's also e to the x to the another thing. We'll call it r. In that situation, you multiply the exponents. So this is e to the x times r. All right? Now, you could say these are just basic facts that everybody knows, but actually we can derive these using our properties that we already know of the ln, because after all, that is the definition of this e to the power whatever is the inverse of ln. So let's just talk about the first one. These are all easy to prove in this way. Write this logarithmically instead. This will look a little bit weird, but to show this, I will just say this is equivalent to, can we say, what will this look like if I write it in the logarithmic form? Here I have e to the something equals all of that stuff. I would like to write this instead in the logarithmic form. Yeah, you want to try? ln of everything on the right, okay,
Plus x plus y.
equals
X plus y.
x plus y. Great. This is the logarithmic version of that formula right there, all right? And if my intention is to prove this formula right there, it's the same as if I could prove this, right? Because these 2 things are saying the same thing. This is a very weird way of writing it, but they are equivalent, and so we'll prove this one instead. So we'll prove this. This is a standard trick in all of mathematics if you want to prove something. Sometimes it's easier if you rewrite it somehow in a weird way and then prove that other thing. All right, we'll prove this. And how do we prove this? Let's just start with the left-hand side. ln of e to the x, e to the y. Can you do anything with that to simplify? What can you do? What'd you say? Addition, yeah. When I have log of something times something, this is multiplication on the inside of the log, it turns into addition of the 2 logs. So this is log e to the x plus log e to the y. That was the multiplication and addition property of the natural log. And then what is ln e to the x? Those are inverses, so this is just x, and this is just y. And that is, I said, we'll prove this, that's it, right? I just did prove this. Shun. All right? That's what I said we needed to prove, this right here. And it follows from the multiplication and addition rule of the natural log. All right? If I was talking to someone who already is on my wavelength about this, I would say, like, why is this true? Why is this plus and multiplication property true of E? It's because of the multiplication and plus property of the ln. And it goes the other way around. The ln has multiplication on the inside and turns into addition on the outside. Here we have addition on the inside, which turns into multiplication on the outside. But the reason that they are both true, they are both expressing the same fact, just one is written in the logarithmic form and one is written in the exponential form. So this, in a sense, this rule right here is really like the same as the rule about log of a times b equals log of a plus log of b. They're the same thing, just written in one way or the other using the inverses. All right, these ones over here, I don't think we need to write the proofs of, but you would do them in exactly this way. Write them first as a logarithmic and then use the appropriate rule from the logarithm. All right. Great. So this is all I wanted to say about basics of e to the x. Maybe we haven't really said anything about calculus today. Maybe we should talk about derivatives a little bit. Everybody's favorite thing about e to the x? Derivatives with e to the x. If someone just asks me at random, like, what's so cool about what's so great about e to the x? Actually, I would probably respond with something about the derivative of e to the x. Surely you've seen this before, and you know that e to the x has a very nice derivative formula. I would like to see where that comes from. And again, we're going to do it the same way about, like, let's write it in terms of a logarithmic form instead, because we already know about the derivative of a logarithm. So if I write y equals e to the x. So for y equals e to the x, what is dy dx? I would like to somehow leverage the knowledge we already have about ln x to find the derivative here. And the appropriate way to do that would be to just write this instead in the logarithmic form. So the logarithmic form would say ln x equals y, right? That's writing it, ln y equals x, sorry. It is easy to confuse these. Make sure the thing which used to be on the inside should now be on the outside, and the thing which used to be on the outside should now be on the inside. That's what inverses are all about. All right, this is the logarithmic form, and now I'm going to take the derivative of that because we already know what the derivative of ln is. So here I'm going to do, and because there's a y in there, this again is actually the implicit derivative. The imp deriv, as they say. I'm going to take the derivative on both sides. On the right side, what do you say? Derivative of x? You could show me the fingers. It is 1, the good one. And the derivative on the left side, ln y. We talked about the derivative of ln last time, 2 times ago. The derivative of ln of whatever is just 1 over whatever, and then times dy dx. All right? This is actually very much like the logarithmic differentiation trick that we did at the end last time. And now I would like to write my answer in terms of, like, solve for dy dx. You just multiply the y across. So, come on now. So dy dx equals y. And what is y? We said at the very beginning, y equals e to the x. All right. This is the big fact that everybody knows. So if you begin with y equals e to the x, the derivative is, again, e to the x. And this is the great derivative property of e to the x. So I will write this in a box. You definitely need to know this, although you probably already did. The derivative of e to the x is e to the x. This is the special thing about the function e to the x. If someone just asks me on the street, what's so great about e to the x? This is what I will tell them. The derivative of e to the x equals e to the x. If they then ask, what is the derivative? I will say, I'll tell you when you're older. I don't know. I don't have any response to that in a simple way. All right. But this is the good property of the function e to the x. All right. More often, this by itself is not terribly useful because usually you have a more complicated thing involving e's. So more likely, I will say we usually want to use this with the chain rule. And as usual, our book has a formula written out for that. So if you had some other stuff inside of the e, you would have to use the chain rule. The chain rule says you do the derivative of the outside thing first, which is the e. Now, when you do the derivative of the e, you're just going to get the same thing again. And it really should be the same thing up there. Don't put g prime of x up there because I am getting the same, the chain rule says take the outer derivative, leave the same thing on the inside, and then separately times derivative of the inside is like so. All right, so this is also a formula that you will see in the book. I don't typically have this memorized. I have that one, the first one memorized, and then I just remember you always have to do the chain rule unless it's just x. Even if it is just x, you can still just do the chain rule. All right, so for example, simple example like that would be derivative of e to the 3x squared plus 7x. The answer is you get the same thing again, e to the 3x squared plus 7x, and then times the derivative of the inside of the exponent, which in this case is 6x plus 7. All right, so that's all there is to it. This is the chain rule with e to the x. All right, these I think probably you've done these already in your youth. Let's just try. I have a bunch for you to try. See what you think. Each time, take the derivative. How about e to the root x, e to the sine x, x times e to the 5x, and e to the, this is a crazy one. Let's get crazy with it, like that. Those are four different things. Everybody's looking good.
When you do the product rule, when you do the two functions, So
Mhm.
like for that one, it would be like the derivative of x times e to the 5x. Then when you do derivative, keep x, you do addition.
So you said derivative of x times e to the 5x?
Like,
Is that what you said first?
yeah.
Yeah, and then you
Would
go
this-
plus.
Would this be a plus sign?
Yes.
Yeah, right.
Yes.
Yeah.
All right, can we talk about these? Everybody seems to be doing just fine with these. So the derivative of this one is, in all cases, you get the same thing again, and then times the derivative of the inside. The inside is x to the 1/2, so this would be 1/2 x to the minus half. That's how I would write this. Everybody feel good about that? I think this one, derivative e to the sine x, this is perhaps even easier. It's just this, right? E to the sine x, and then times the derivative of the inside. Derivative of sine is cosine, so you just get that thing. These last two you have to do a little bit more work for. What? No. Yeah, I said no. All right. I think I hit the record button, which I don't want. Here, the derivative of this. This one is a little more complicated because you got to use the product rule. Everybody realized that as I was walking around. There is multiplication. X is the first part, and then times e to the 5x. So the product rule, there's a few different ways to write it, but I always do the first thing as is times the derivative of the second thing. That would be this. So this is x, which was there to begin with, and then times the derivative of that, which is e to the 5x. Same thing again, times 5, the derivative of the inside. And then plus, that's the first half of the product rule, plus the second thing, as is, times the derivative of the first thing. The second thing is e to the 5x. The derivative of the first thing would be just 1. So that's the derivative there. That's a product rule. Any questions about that one? And then the last one requires a quotient rule, although not right away. When I do the derivative of this e thing, I get the same thing again. E to the 3x over x squared plus 1. And then times the derivative of the inside. The derivative of the inside would be the quotient rule. And this is a big quotient rule thing. I hope you all remember the quotient rule. It is the bottom times the derivative of the top, which is 3, minus the top, 3x, times the derivative of the bottom would be 2x, all divided by the bottom squared, like that. I hope you got something like that. That's the quotient rule. Any thoughts about that one? As I was going around, it looked like everybody was feeling good about that. All right, yes?
Actually, what is the third one simplified? The third one down.
This one here?
Yeah.
If you wanted to, I would say this is what it simplifies to. If you want to go even further, this times 1 you can ignore, and I would write 5x here. I mean, if you want it to be all tidy like, something like that. Or you could write it plus the other way around, e to the 5x plus 5x e to the 5x. Something like that. Yeah. I suppose you could factor e to the 5x out of both of these. I don't know why you would, but it's the same as e to the 5x plus 1. I consider that to be weird, but it's the same. All right, great. What about, so these are all about derivatives of e to the x. Let's just briefly talk about integrals of e to the x. I'm kind of breezing through this because I assume that you've seen this stuff before. How about, this is the derivative of e to the x, is e to the x. So what's the antiderivative of e to the x? It is also e to the x. The antiderivative of e to the x dx is e to the x plus c, all right? Because the first one says the derivative of this one is that one. To write it the other way around, it means the antiderivative of this one is that one. But these are all the same, this one and that one, so you get e to the x, integral e to the x dx equals e to the x plus c. This, again, by itself is not all that, doesn't come up all that often. Usually there's like more stuff in there. So here is, let's just try one example with using that. I mean, this, so I'll put it in a box. You definitely need to know this formula, but it's not much to it. Let's try this one. So this is an integral involving e's, but there's more going on than just the e to the x. Would anyone like to suggest a strategy here? Yeah? Yeah, we should do the U substitution. That is basically the only strategy we know yet in this class. And since I see things being multiplied inside here, there's really no nicer way to do this. So I'm going to do the U substitution. U equals, oh, sorry, I should have asked somebody. What do you want for the U? Choose the inside, right? That's what we always pick the U to be, almost always at least. And in this case, you should choose the inside of the exponent, u cubed minus 1. And then the du shall be 3x squared dx. All right? And I feel good about this because I see x squared and dx as part of the du, and I see x squared and dx over here. So I think this is going to work out. What do we get? When we plug everything in, it's going to say e to the u. That's the e there with the u in the exponent. And then what's left, apart from e to the u, the other stuff is x squared times dx. And x squared times dx, we can divide the 3 here. 1/3 du equals x squared dx. So this becomes integral e to the u times 1/3 du. Pull the 1/3 out like we always do. There you go. Now the substitution is finished. This is pretty ordinary U substitution. All right. Next step, we do the integral. Integral e to the u is e to the u plus c. So this turns into that. And then my final answer would be replace the original variable like so. All right. Any questions about that one? All right. Sometimes looking at this one, maybe a little confusing. What happened to the integral sign here? It looks like I kept on writing the integral sign for a while, but then I just didn't write it anymore. Yeah, actually, this is the step in which I really did the integral. It looks like nothing happened, but that's because the integral of e to the u really is e to the u. So in this step here, we did the integral, and basically nothing else happened, although we got the plus c at that point because we did the integral. All right, integration with ease. Remember that joke that I told about a half hour ago? Still got it, right? All right, this is integrals with the ease. We got 7 minutes remaining. Maybe I could tell you, this is something that I mentioned last time or maybe 2 times ago. I actually don't know if I mentioned to you all. You know I have two sections of this class. I know this is like talking about your ex-boyfriend, but I think I told this to the other class and not you guys, sorry. I have, or maybe I told you guys, there was one time in my life, in my real life, when I used logarithms in my real personal life. I would like to tell you that story now. We're ready now, I think. We have 7 minutes remaining. This happened like about 10 years ago. I was diagnosed with a genetic disorder, which I still have because it's genetic, called, this is my little HIPAA moment. I have, it's called hemochromatosis. Anybody out there also have hemochromatosis? You may and not know it. This is a genetic condition, and what it is there is some kind of it's a disorder of the blood, and there is some kind of mechanism in the blood which removes excess iron from your body. So like iron is an important, nutrient for everybody to have, but if you have too much iron, this is actually bad for you. And iron also, I'm sure you all know, iron is a chemical element on the periodic table. That means your body cannot make iron by itself. And also your body cannot break down iron because iron is not it's not a chemical compound, it's an element. Like the only way to break down iron is like to throw it into the sun or something, like with a nuclear reaction. So all the iron in your body is there because you ate something. And the only way that iron leaves your body is, the way that things leave your body. People with hemochromatosis, there's like a natural chemical process by which your your blood kind of like grabs extra iron and sends it away out of your body. And people with hemochromatosis, that system is messed up so that, like for me, because I had this, iron does not leave my body at the appropriate rate, all right? So if you live like this for your whole life, like it doesn't actually have many bad effects unless you live like for decades without knowing that you have it, and then iron will accumulate in your liver and you will die because of it. So it doesn't have a lot of symptoms until your body is like seriously damaged by it. And like if you have like a grandma with orange feet, this actually can happen. Like rust can appear on your skin if you have way too much iron in your body. And this means like you are about to die of liver failure because of this. Anyway, I found out that I have it because by some ridiculous fluke, both of my parents have it. And so I was guaranteed to have it because it's a genetic thing. It's like a classical kind of dominant recessive. It's a recessive genetic trait which exists pretty much only in Northern European white people. So you know, Fairfield University could be sort of a hotbed for this condition. It is white people have this because people with too much iron in their body are actually resistant to the bubonic plague. So back in the old days, it was beneficial to have too much iron. So I am resistant to the bubonic plague, but it's not a good thing anymore. But that's why this is. It's not all that common, but the statistics are about 1 in 40 white people are carriers of the recessive trait, which means if you do the math, about 1 in 800 white people actually have hemochromatosis. So for me, like it was very unlikely that both of my parents actually have it, but it's true. And they didn't meet because of it. They found out after. But anyway, so there is a treatment though. Apparently, not many people are working on this, but there is no drug that you can take that will just like send iron out of your body. Most people want to get more iron. Actually, hemochromatosis is less harmful to women because, I don't think I need to get into the details, but there is a natural process by which women lose blood, and the blood, of course, contains a lot of iron. And so like there's this other process by which women naturally lose iron, and that's why women tend to be more anemic, like they tend to need more iron. But anyway, for men, there is no such procedure. But the treatment, there is no drug for this to remove iron from your body. The treatment to remove iron, I guess, is like inspired by the ladies. Remove the blood from the body. So the treatment is, I go in every so often, they take my blood, they throw it in the dumpster, and there I just lost some iron from my body. That's how it works. There is no, that sounds kind of primitive, but there is no better treatment than that. This is like one of the only medical conditions for which the old leeches was actually effective. Like the leeches would do the same thing by sucking the blood out of your body. I don't think we have time to do the math here, but anyway, the story of when I used logarithms was about when I learned that I had this. They gave me a blood test that showed what this level of iron in my blood was. So at the time when I was diagnosed, my level, this is how it's measured in nanograms per liter. This is like a very small amount of stuff. But anyway, this was my amount of iron, like free iron in my blood. They can draw your blood and do this test. 800 nanograms per liter. This is way too high. So the healthy level is something like 15. All right? And so when they saw this, they're like, all right, you have hemochromatosis. And they said, the treatment is, you're going to come in, we're going to draw blood over and over again until this number just goes down. And it will go down because we're taking your blood and just throwing it away. And my question for the guy was, all right, how many times do I got to do this to get down to 15? And the math behind that involves doing the log. So we'll do that. We'll do the details next time. I'll leave it to you. You can think about what does this have to do with the log?